Bismillahirrahmanirrahim. Greetings. The concept of a function is fundamental in mathematics. Now in this lecture, I'm going to discuss about the analytical link and structural similarities of function and its inverse. Now, my assumption is that the audience are already familiar with the concept of function, different kind of functions in general, and the composition of functions in particular. Now, I have already uploaded a few lectures about this subject of function, and I do encourage you to watch them in case you need to refresh yourself. Now, then the second part of this lecture will be the second video. I will be giving the very same concept, but with the analytical geometry illustration, the second part. And that is to improve your conceptual understanding of the subject and also better comprehending the subject. Okay, then let's get started for today's lecture, shall we? Now, 2 plus 3 equals to 5, and 5 minus 3 equals to 2. They are arithmetically equivalent to one another. One of them undoes the act of the other one, but arithmetically they are equivalent to one another. In contrast, y equals to 2x and x equals to 2y have same algebraic structure. I repeat myself, they have same algebraic structure. The difference is that the rule that corresponds x and y together have been interchanged. The rule has not been changed, but interchanged. Swap. Do you follow me? Now, when I go through the demonstration with the sets of order pair, this subject will become much clearer. Okay, then, let me now stay out of bed, and I have some handouts to hang them from the board, and we go over that in writing rather than talking. It does improve your kind of imagination when I talk, but also you need to see it visually. Okay, then, let me do that if I may. Let me zoom this one if I may. Okay. I guess I don't need this part of it. I come back, I read it if you may. And let me go over that. Now here, I have 2 machines. One of them, whatever you put as an input, he add 3 to that. The other one, whatever you give to him, it subtract 3 from that. Now when we combine them together, which is really the composition of them, that's what the word combining composition of function come from. Look what happened. I give 2 to this machine, he give me 5 as an output. Is that right? The output of this function, of this machine will be the input for this machine. So when I give 5 to this machine, he will give me 5 minus 3, which is 2. He give me the 2 out. And look what happens, the very same 2 that was input for the first machine, when he went through the first and second, he came back exactly the same number, which means the identity of the input number did not change, 2 stays change. So I generalized this idea, and instead of 2, let's say a, which is any real number as a matter of fact, as an input. So when I give a to this machine, he give me a plus 3 as an output, and the output of this machine will be the input for this machine. So when I give a plus 3 to this machine, he give me a plus 3 minus 3, which means a again. You see the a comes back. All right? Now, I have written something. I'll go through that quickly. I already mentioned it just for the sake of it. Now, 5 plus 3 and 5 minus 3 are what? Are arithmetically equivalent, even though they are phrased differently. One simply reverses the action of the other. Okay, so good. So let's go now to the next one, if I may. Let me go and see if this needs to be zoomed. Yeah, just 1 second, please. Looks good, huh? Okay. Now it's the very same subject concept. I put both these machines inside in one box, which from the outside it looks only one machine. But inside this box, there are two machines. So the first one, when I give 2 to that, he give the output 5, and then the 5 will be the input for this machine, so the 2 comes out. So these two, again, I repeat one more time, is the box from outside. When you look, it looks only one box, but inside that there are two machines that they behave in a kind of reversing one another. Now, in contrast, let me cover this one so that we can concentrate on that. The very same is going with this one. Now, the input for both are x, all right? X is the input. Now, I give 3, the y will be 6, is that right? The output will be 6. The output goes to this machine, and when the x is 6, y must be 3, because 3 times 2 is 6, is that right? So the 3 coming from the outside to the big box, he went through 2 machines inside that box, and this very same 3 came out, which we call it identity. You follow me so far? Okay, now let's go and see from the point of set notation. Let me go and see if it is zoomed, or I need to adjust it a little bit. Okay, now look what happened here. Please pay attention here, it's something very interesting is going to happen. Now here, y equals to 3x. All right? Y equals to 3x and x equals 1/3 of y, they are equivalent. They are equivalent. For the time being, let's say they are equal. What did I do? I just multiply both sides by 1/3. Is that right? When two things are equal, when you multiply both sides by the same thing, if that something is not 0, the both sides will be equal again. Do you follow me? So the equality is preserved when you multiply both sides by the same thing. Now, look what happened. This and this, they have same set of order pair. Just try a few of them. For this one, when x is 1, y is 3. Is that right? And for this one, when x is 1, y must be 3, because 3 over 3 is what? Is 1. So for this one, when x is 2, y is 6. For this one, when x is 2, y must be what? Y must be 6, because 6 divided by 3 is 2. Do you follow me? They both have same set of ordered pairs. So let's call it equal. I don't like to use the word equal because they do not look same. The better word to use is equivalent, but let's call it equal for the time being for a better comprehension. Now, let's look at next one now. Now, I interchange x and y. The algebraic structure of them remains same, but the rule that corresponds x and y together is what is interchanged. Not changed, but interchanged. All right? The rule has been interchanged. Now, look at the set of ordered pairs of this one. When x is 3, y must be 1. Is that right? When x, look at this one now. When x is 3 here, when x is 3, 3 over 3 is what? 3 over 3 is 1, so y is 1. So if you try any other numbers, you put for x, and the y will be the same for that. So they have same order pairs. So that means what? That means this is equivalent to this, but let's for the time being call it this is equal to this. Because I didn't do anything, I just multiply both sides by what? By 1/3. Now here comes the moment of truth. Now please pay attention, it's very important in this case. Now, this one is the inverse of this one in a sense. By inverse, I mean the rule of corresponding x to y has been interchanged, and by inverse, I mean the sets of ordered pairs has been swapped, has been what x and y in a sense they have been, the word will be swapped, is that right? So they have been interchanged. So this is the inverse of that. You agree with that, huh? But this is equal to this. We just showed they have the same set of ordered pairs. So if this is equal to this, and this is the inverse of this, therefore this must be the inverse of this one. Do you follow me? Now the reason I go through that, because I don't want to hear that you just change x to y and then solve it for y in order to find the inverse. And that is correct, but it is kind of recipe following. That is a step following. And there is no mathematical deep into that to explain it. And that is exactly what the explanation of that is, and that is what exactly mathematics should be. So my advice to all my students is do not follow recipe. Do not follow steps. Always demand for justification and always dive more deep into the subject to see where they come from and why they work that way. Okay, now let me go to another which is exactly the same but a different example that we already mentioned it verbally. This is just kind of repeating a reality. So repetition is a very good way to learning from. Now, let me cover this one. Now, y equal to x squared. All right? This is my function. Now, these two are equivalent. Again, let's call it equal. Because I have taken a square root of both sides. When two numbers are equal, their square root is also equal. The converse of that is not true, but we are not talking about the converse anyhow. So these two are equal, therefore the square root of them are equal. And the square root of x squared is absolute value of x. Again, when we go to the next lecture, because I'm putting my assumption on the x and y to be on the first coordinate, to be both positive, so I'm not going to be that kind of rigorous and mathematically kind of meticulous to say, okay, this should be absolute value of x. So I'm taking the positive side of that. Now look at the look at the ordered pair points. When x is 2, y is 4. Here it is. When x is 2, y must be 4 because the square root of 4 is 2. When x is 3, y is 9. Is that right? Now here when x is 3, y must be what? Y must be wrong because a square root of 9 is equal to 3. So these two are equal. Again, I'm using the word equal for a better comprehension. And so because they have same set of order pairs. Now look at this one now. Exactly same kind of analogy. Here, I interchange what? I interchange x and y. So the rule that corresponds x and y has been interchanged. Now, these and these are equivalent. Again, I repeat myself, let's call it equal. What I did, I just took a square root of both sides. Do you follow? Exactly like the previous one. Now, if you plug few numbers, you will see that is the way. When x is 4, y must be 2, because 2 squared is 4. When x is 4, look at that, a square root of 4 is 2. So if you try other numbers, definitely go 4. So these two, they have same sets of order pair. So they are, let's call it equal. Now here comes the moment of truth. Now listen carefully because it's very interesting. Now look what happened. This is the inverse of that. Inverse in what sense? That rule, the rule that corresponds x and y has been interchanged. That is one way to look at it, as calling them inverse. The other one is that from the order pair notation, as you notice, they have been interchanged. You see that? You see that clearly over there. So this is the inverse of that. We 100% agree. This is equal to this. All right? I'm using again the word equal. This is equal to this. Since this is the inverse of that, therefore this must be the inverse of this one. You follow me? So this is the inverse of that. So I'm not just saying change x and y and solve it for y and you get the inverse. So where is the mathematics? That is nothing but recipe following, and I do not teach that way to my students. Okay, now let me go to the next one, if I may. Now here, I use the f of x instead of y because we are already familiar that f of x stands for a function of x, and we are talking about functions. So f of x equal to 3x, the first example we made. Now, f circle, f inverse of x, this is the inverse of that. We went through and we know where does come from. That is y equals to 1/3, end up to be the inverse of y equal to 3x. So I use this notation instead of y. Now look at this one carefully. Here is the box that I was talking about. Inside the box is the two functions that they are being composed together. You see that? And how do these functions, they compose to each other? This is the way they compose. So this is my big box that I mentioned it in the past. Let me show it here. You see that this one, the box that I had? This is exactly that the box is a composition of two functions inside that. And inside that there are two functions that they are composed together, and whatever you give to it, the output of this will be input of this one, and the very same x comes out. Just try it for yourself. Do you see that? And the very same goes the other way around that we tested before. Again, this is my box, which means inside the box is a composition of two functions, which is a function of its own, and then that's what happened. The output of one will be the input of the other one, and the very same x comes out of it. Do you see that? So please pause, contemplate, and you have access to your computer, and that is much advantage to learn it really. Okay, and the last one, if I may, which is similar to this, just for the sake of the argument and practice, let me give another one. And that is the one that we already mentioned, we covered it. Now here, exactly same thing. My f of x equal to x squared, and then we know why the inverse of that, y equal the square root of x will be the inverse of that. We have gone over that in previous lecture, just a few minutes back. Now, this is my box. The composition of two functions. Inside that, the output of one of them is the input of the other one. And by doing that, when we compose these two functions together, the very same x that was input for this will be output. So we call it identity because the identity of that number is not changed. It's very interesting. Okay then, let me now zoom back and say a few words and close for today's lecture, if I may. Okay, I do not need this one. Okay then, I thank you for watching. I always say at the end, I wish you all good luck and prosperity and good health. And I repeat myself for the coming lecture that I'm going to discuss the very same subject but using analytical geometry, just for the kind of visual aid in a sense, and pictorially because it improves your comprehension and also improves your conceptually understanding from the subject. So please do not hesitate to watch the second one coming soon, and hopefully all these videos are productive. I'm not doing that for money, and my pleasure is for to have that they be access, that the public can have access to that, and they can learn from it. Of course, first is for my own fellow Americans, and second is for my fellow man wherever in the world they are, and hopefully they will learn from them, and they will have some good product from them for their mathematical enhancement, for mathematical maturity. Okay then, for the second time, I thank you for watching, and again and again and again, I wish you all prosperity and good health, and please stay and remain safe, and accept my army salute. So long.